Hey everyone, I wanted to do the next unit, which is all about dynamics and dealing with forces. We're going to start off talking about Newton's laws of motion, and that's going to act as the foundation for everything we're going to talk about from here on in this unit and future units. So we have to start off with our definition of forces. A force is an action or interaction that causes a change in motion of an object. Now, if we go back to the first unit of kinematics, what is a change in motion? Well, a change in motion in this specific case is referring to things like increasing your speed, decreasing your speed, or changing your direction. In other words, a force causes an acceleration. Forces are vectors because direction matters, and they're measured in newtons. This is in honor of Sir Isaac Newton, who came up with the concept of forces and the three laws of motion. There are a few fundamental forces, so we're just going to talk a little bit about the concept of forces here, as well as talk about something called free body diagrams or FBDs. Now, there are four fundamental forces, and basically all forces will be a variation of these four forces. There's the gravitational force, which is a very long range and attractive force that acts between two pieces of matter. It's the weakest by far of all the forces. Then we have the electromagnetic force. This is actually the more common force. Technically, all the other forces we talk about are forms of that electromagnetic force. This is caused by electric and magnetic effects, and it's basically between magnets and charged objects. It's extremely strong, can also act very long range, and can be either attractive or repulsive. Then there's other two which we really don't talk about in this class. They only really appear at the nuclear level. We have the weak force, which is very short range and is responsible for radioactive decay. And then there's the strong force, which is by far the strongest of all the forces. Again, it's also very short range. It only works at the nuclear level, and it's responsible for holding the nuclei of the atom together. If you recall, in chemistry, the atom has a bunch of protons together. Those protons don't want to be together because positive charges repel, or I should just say like charges repel. So what's going to overcome that repelling electromagnetic force? It's the strong nuclear force keeping them together. Now, that's the four fundamental forces. However, I'm just going to also run through some of the more common forces. Now, one thing I do want to point out is that throughout this unit, we're going to be constantly referring back to these and relearning them and seeing them in their different effects. So don't feel like you have to memorize everything right this second. This is something that we'll cover throughout the unit. Uh, so the I'm going to do this in order of commonality. So by far the most common force is the force due to gravity. This is the force that keeps us on the earth. It's always present, and it's sometimes referred to our weight. Weight and mass are not the same thing, so please do not confuse them. Weight is the force of gravity, not mass. Then the other more common force is the normal force. You'll notice here that we put little subscripts on these. All these forces are usually represented with the capital letter F, with subscripts referring to what specific force it is. So F of n is the normal force. This is the contact force that we feel whenever we touch an object. The reason we call it the normal force is because the force always acts perpendicular to the surface. If you go back to math, that is what the term normal means, perpendicular to something. So when you're sitting on a chair, the chair is pushing you up. That is the normal force from the chair. If you're leaning up against the wall is pushing you away from the wall. That's the idea of the normal force. So it's anytime you're in contact with the surface, it will always push you away from that surface. There's a tension force, which only really appears whenever you have a rope, a string, a cable, anything like that. It's typically a pulling force. So if you are attached to a rope, the rope is pulling you up. That is a tension force that's pulling you. Then we have an applied force. This is just referring to a force that any person applies onto an object. So if you start pushing onto an object, then there's an applied force. Now, it could be either pushing or pulling, so it really depends on the scenario. One thing I do want to point out about the applied force is that it only refers to when the person is actively touching and applying the force onto it. For example, if I was pushing onto a block that was pushing onto a second block, you would not say that I was applying a force on that second block because I'm not physically touching it. I'm applying a force indirectly to it, but there's no applied force on there. This is going to matter when we start doing FBDs and start solving problems. Frictional force is a force that usually opposes motion. It's usually dependent on two surfaces touching. Uh, For the most part, you're going to assume that it's not present unless specified otherwise. Usually, this means that what by specifying, I mean that they either mention that this is a real life scenario, like a lab scenario, or they refer to the surface as being rough or something like that. Those are indications that there's going to be friction on the surface. Centripetal force is a force that acts on an object when it's moving in a circular path. Centripetal means circle. Now, one thing I do want to point out is this actually won't be covered in this unit. This is actually going to be covered in the next unit, which is all about the big gravitational forces, planetary motion, and circular motion. These are not so common forces, so they really don't come up too much. There's another gravitational force. You might be wondering, how is this different from the force of gravity? It isn't technically. It's not different. However, it's used in a different concept. This gravitational force is still the force between masses, just like the force of gravity is. But the force of gravity that we talked about before is usually referring to the force that you experience when you're on a planet, because that's just makes more sense. This is the gravitational force between any two massive objects, or any two objects in general. So a lot of times you would use this when you're referring to things like the force between two planets, or between the planet and the sun, or even two protons. But the force of gravity is usually referring to my my weight on a planet, or on Earth. Then there's the electrostatic force. We're actually not going to be covering this in this class. We do cover it in the region section. So after the AP, we're going to quickly jump ship into electrostatics. It's really straightforward and easy. It's only between charged objects, either attractive or repulsive. It's very similar to the gravitational force equation. We actually do not talk about the magnetic force. I think the only thing you really need to know about it, again, it's in the regions concept, is that it's between magnets, and it's again attractive or repulsive, but you don't do any math with it. Now, this leads into one of the most important aspects of the dynamics. A lot of times when people are struggling in dynamics, they wonder what can they do to improve their concept, their understanding. And my go-to statement is always start with the free body diagram. Always try to draw free body diagrams. It helps you visualize and organize what's going on. So basically, what a free body diagram is, it's a very quick sketch of the object, free of everything outside, and it basically shows the direction of all the forces. So let's say we had a scenario where we had a fireman lifting up a boy using a rope. The boy has some weight of, well, let's just say 500 newtons, and we want to draw an FBD. So we're drawing an FBD on the boy. So the boy is going to start with a box. Everything in this class is a box. We are not artists. We're not going to spend too much time drawing stuff. Everything's either a box or a circle or just a dot. In fact, a lot of times when you're being tasked to draw FBDs, sometimes they actually just leave a dot there and you draw arrows on the dot, because it honestly doesn't matter. Now, we do know that there's one force acting on this boy because it's always acting on an object. It's the force of gravity, and the force of gravity always pulls an object down. So I would draw an arrow going straight down, and I'd usually label it with the force Fg. Then, well, the boy is being lifted by a rope, so that rope is lifting him up. So then there would be an upward force, and that would be labeled as F of t. So this is what my FBD would look like. So this is the first question. Answer it. All right. So they want to know, what is the direction of the normal force. The normal force acts perpendicular to the surface, and it pushes it up this way. So the only one that looks like that would be choice 3. All right, now there is one thing that I want to make sure that you understand about free body diagrams, and it's that when you draw the forces on it, you want to make a habit of drawing the forces so that they reflect their relative sizes. Now, you don't have to draw the arrows to scale, but if you know that there's one force that is bigger than another, you want to make sure that you make that arrow bigger. However, you do want to make sure that you try to exaggerate that size. So, for example, it would look something like this. So if I look at this FBD, I automatically know that this arrow is bigger than this arrow. Now, I had mentioned before that a lot of times you're going to be drawing FBDs on in tests and exams. Uh, the one thing that I wanted to point out is that a lot of times when you're drawing those FBDs, they're going to have a grid paper. So they actually do want you to draw the arrows to scale, relative scale. Um, Not in the sense of the idea that, okay, you want to make sure that one arrow is 3 times bigger than another, but the idea that if there are two arrows that you know for a fact are going to be the same value or equal to each other, then you want to make sure that they're the same number of boxes long. So, if you have one arrow that's 2 boxes long, then the other arrow should also be 2 boxes long to reflect that they're equal in value. If you know that there's a force that is going to be, then you want to make sure that it's multiple boxes bigger than that. So just be careful with that. We'll do problems in class later. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.